Okay, so having gone through the properties of signals uh, and the transformation from time to frequency and vice versa, so we will now summarize the properties of blocks. So in general, we'll consider two properties, that is the linearity and time invariance. So linearity for a given map from input to output is a property of the system which satisfies the given condition, that is for all u1 and u2 the mapping of the combination of these two would be the combination of individual responses, and similarly g of alpha u equal to alpha times g of u. So again a reminder that these are the properties of a block or system that is a map and not of any signal. These are some practice problems, answers and solutions which are given in the end of this PPT. So the second property is time invariance. So the condition is for a map from G to Y to be invariant for all tau G of u of t. If this map is the definition of the map, then it should imply that the map of u of t minus tau is y of t minus tau. First it would appear trivial and just a change of variable, but this requires attention and proper understanding of concepts. So again these are some practice problems, solutions of which are given in the end. So and a special class of operators which show both linearity and time invariance are called LTI operators. L for linear and Ti for time invariant. So we'll see some important results. So for an LTI operator which transforms the input to the output, so consider the response for impulse input be h of t, that is h of t is the impulse response for u of t equal to delta. So this is the expression. So now using this relation we can get the output for any general input function. So the main concept uses the any function. Suppose u of t is a general function. This can be represented as sum of small segments, each of uh, thickness delta, and the general expression for a segment is given by u k delta, and the delta function shifted by some k delta times the delta. So basically this is the delta function. It has been so it has thickness delta and height of 1 by delta to give area 1. Now it has been time shifted and multiplied by delta to make its magnitude equal to 1, and to shift it by k delta. Now it has been multiplied by u of k delta to give the value of the function at that segment. So using this relation we can get the general output for a general input as this, which is known as the convolution of the input multiplied by the with the impulse response, convolution of input with the impulse response, and the proof is given as this. So as discussed, uh, the output is the output of impulse input is the impulse response h of t. Now shifting using the time invariance we get this result. By linearity, for multiplying by delta, the delta would come out. Again similarly for u of k of delta, the multiplication of this with the initial result. Now limiting delta to 0 and taking this summation for all k. So this is similar to the derivation of the Fourier transform on both these sides. So as discussed, this is the sum of each segments, which would in turn give the entire function, and this conversion is similar to the Fourier derivation. So this turns to integration since for all delta and k from being from minus infinity to infinity. So basically it takes every value of tau from minus infinity to infinity, and this represents t minus tau, and this turns to del tau. So this is defined as the convolution of the input with the impulse response, and by change of variables this can be proven to be uh, uh, interchangeable. So this is the final result. Now we have a general output for a general signal. So hence if we know the impulse response, we have the output for any functions. Now here are some important results which we should keep in mind. first would be for a general sinusoidal input e to the power j omega t, we get that on substitution uh, it has been multiplied by a complex number. So for input sinusoids, uh, it it gets multiplied by a complex number, so suppose represented by a e to the power j5, and hence changes as such. So this is the multiplying factor, and this is the phase shift. Also, a linear constant coefficient ODE will always form an LTI. So a LCC ODE of this form would always form a LTI system. Note that there are no constant, hence this is linear as well as time invariant. So these are the solutions to the problem. Thank you.